Hi everyone, this is Dr. Saida Fallofini from Cal Poly Pomona. In this video, I want to talk about constructing decision trees when we don't have all the information that we need readily available in the problem statement. So we need to construct and build some of the information that we need. Before I jump into discussion related to decision tree, I need to review some of the rules related to probability that we will use in this video. The main one is conditional probability. So if you remember from statistics, probability of A condition on B, meaning that what is the chance that event A happens if we know event B has already happened, equals to probability of A intersection B divided by probability of B. I can also rewrite this as probability of A intersection B equals to probability of A condition B multiplied by probability of B. Similarly, I can write probability of B condition A equals to probability of B intersection A divided by probability of A. And I can rewrite this equation as probability of B intersection A equals to probability of B condition A multiplied by probability of A. On the other hand, from probability rules, we know that probability of A intersection B equals to probability of B intersection A. So when the left side of these two equations equal to each other, then the right side of these equations equal to each other as well. So that means then probability of B intersection A condition probability of A equals to probability of A intersection B multiplied by probability of B. So this is basically the main rule that we will use in this type of decision tree. We can generalize this conditional probability a little more. So as you can see below, so if I have the sample space E, that sample space E contains all the outcomes of an experiment, and I divide this sample space into three different events, event A, B, C. As you can see, event A, B, C, they have no intersection, and their sum together forms the whole sample space. So I can write E equals to A plus B plus C. And I also can write E as E intersection A plus E intersection B plus E intersection C. Why? Because E intersection A equals to A, E intersection B equals to B, and E intersection C equals to C. So the second equation is definitely E equals to A plus B plus C. Okay. Now, if I use the probabilities over this equation, since these three events have no intersection with each other, then I can write probability of E equals to probability of E intersection A plus probability of E intersection B plus probability of E intersection C. Okay, and then using the conditional probability rule, I can write this as probability of E equals to probability of E condition on A multiplied by probability of A plus probability of E condition on B multiplied by probability of B plus probability of E condition on C multiplied by probability of C. The example that I want to talk about is related to a farmer who needs to decide to whether plant corn or wheat at his farm. The yield that he will observe depends on the weather condition, if it's going to be cold or warm. If he plant corn and the weather is going to be warm, he earns $8,000. If, on the other hand, if he plants corn and the weather is cold, he earns only $5,000. If he plants wheat and the weather is warm, he earns $7,000. But if he plants wheat and the weather is cold, he earns $6,500. In the past, about 40% of the years have been cold and about 60% of the years have been warm. Before he makes the decision on planting corn or wheat, he can pay someone to do a weather forecast for him. He can pay $600 to someone to do a weather forecast, and if the year actually is going to be cold, there is 90% chance that the weather forecast also says it's going to be cold. And if the year is actually going to be warm, there is 80% chance that the weather forecast predicts it as warm as well. We want to know what is the decision that this farmer is going to make, and also what is the expected value of sample information. Here is the summary of a problem statement. We want to know if we have to plant corn or wheat. And here we are showing the earnings that we will have if we plant corn or wheat, and if the weather is going to be warm or cold. We also know that we can potentially pay $600 to an expert to do a weather forecast for us. Based on the previous data, based on the previous years, we know that 40% of all years are going to be cold. So that's the probability of a year being cold, or probability of C is going to be 40%. So I just use the notations that I will use when I construct the decision tree. 60% of all years will be warm. So the probability of warm, or probability of W, is going to be 60%. We also know that if a year is actually going to be cold, there is 9% chance that the forecast will predict cold as well. So that's probability of forecast saying that it's going to be cold if the year actually going to be cold as well. So probability of forecast saying it's going to be cold, condition that the year is actually going to be cold, that's 90%. Okay. We also know that if the year is going to be actually warm, there is 80% chance that the forecast is going to predict it as warm. That means probability of forecast predicting warm if we know the year is actually going to be warm, or probability of forecast warm if the year is actually going to be warm is 80%. Okay, so these are all what I got from problem statement, and I just try to write them as probabilities so that we have a easier time when we want to use it in the decision tree. And we want to know what is the best decision and what is the expected value of sample information. I strongly recommend you at this moment to pause the video and develop the structure of the decision tree. What is the first decision that this farmer is facing? To pay for the forecast or not to pay for forecasting weather? If the farmer decides to pay for the forecasting of the weather, what would be the outcomes? The forecast would say that this year is going to be warm or this year is going to be cold. Okay, so let's assume forecast says, oh, this year is going to be warm. What is the next thing? So still we have to make the decision. Are we going to plant corn or plant wheat? Similarly, if the forecast says this year is going to be cold, we have to decide, are we going to plant corn or plant wheat? Okay, let's assume we decide to plant corn. What would be the outcomes that we will observe? If we plant corn in that year, then the weather, it may turn out to be cold or warm. Okay. Similarly, if we plant wheat, then the weather may turn out to be cold or warm. And we know that under each one of these scenarios, we are going to observe a different yield. And similarly here, if the forecast says cold and we still go ahead and plant corn or wheat, we may observe any weather condition in the actual scenario. In the actual year, we may observe any weather condition, and our yield will be different under different weather conditions. If we decide not to pay for any forecast at all, what is next? We still have to decide if we are going to plant corn or wheat, and based on each one of the decisions, we may observe two possible outcomes. If the weather is going to be cold or warm, the actual is going to be cold or warm, and under each one of these scenarios, we may observe a different yield. So far we have the structure of the decision tree. Next, I need to calculate the monetary value associated with each one of these terminal branches. So let's see what's happening at the first terminal branch. In this first terminal branch, we have paid for the weather forecast, and weather forecast says warm. We have decided to plant corn, and the actual weather condition has turned out to be cold. In this scenario, we know that if we plant corn and the weather is going to be cold, we observe only 5,000 as our earning. But at the same time, we also pay $600 for the weather forecast. So the monetary value associated to the first terminal branch is 5,000 minus 600. For the second one, we have planted corn and the weather has turned out to be warm. If we plant corn and the weather is going to be warm, we earn $8,000. However, we have paid $600 for the weather forecast. That's $8,000 minus 600. If this terminal branch, we have paid for the forecast, forecast is warm, we have decided to plant wheat and the weather actually has turned out to be cold. In this scenario, we know that if we plant wheat and the weather is actually going to be cold, we obtain only 6,500, and we have paid at the same time $600 for the weather forecast. And if the weather is actually going to be warm, we earn $7,000, and we pay also 600 for the weather forecast. So the monetary value associated with the next 4 terminal branch will be similar to the above. I recommend that you guys pause the video at this point and do the calculations yourself and make sure you get similar numbers. How about this other terminal branch? For this one, we have not paid anything for the forecast. We have decided to go ahead and plant corn, and the weather actually has turned out to be cold. That yields to the earning of $5,000. If the weather actually has turned out to be warm, that yields to the earning of $8,000. And if we plant wheat without doing any forecast, if we plant wheat and the weather actually is going to be cold, we earn 6,500, and if the weather is actually going to be warm, we earn $7,000. If you have paid attention so far, you can see that I have not put any probability values on any one of these branches that come out of even nodes. To be able to do that, first I want you guys to put the probabilities not based on the values, but also using the notations I introduced in the problem statement. So for example, here, probability of forecast saying that it's going to be warm is probability of FW. Probability of forecast saying it's going to be cold is probability of FC. Probability that the weather is actually going to be cold if the forecast has said it's going to be warm is going to be probability of the C, condition on forecast warm. This means that probability that the weather is actually going to be cold, condition that forecast has said it's going to be warm. The next one is probability that the weather is actually going to be warm, condition that the forecast actually has said it's going to be warm, right? The reason that we condition on the forecast is that we already have done the forecast. We know the results of the forecast. So this part has happened. So we can condition on that event. Okay. So this means the probability that the weather is actually going to be warm if we know the forecast has said it's going to be warm. How about this one? This one is probability that the weather is actually going to be cold if we know the forecast has said warm. Probability that the weather is warm if the forecast has said warm. And how about this one? This one is probability that the weather actually is going to be cold if the forecast has said it's going to be cold. So that's probability of cold, condition on forecast saying that it's going to be cold. The next one is probability of warm, that the weather actually is going to be warm, condition that the forecast has said it's going to be cold. And how about this one? This is probability that the weather actually is going to be cold if we know that the forecast has predicted cold. Probability of weather actually going to be cold if forecast says cold. And the next one is probability that the weather actually is going to be warm if we know that the forecast actually has said it's going to be cold. Okay, how about this one? We have not done any forecast in this part, so this is just simply the probability of weather to be cold, probability of weather to be warm, and similar for the last 2 terminal branches. Okay, so this is very helpful. This helps us to see if we have these probabilities from the problem statement or not, and if we don't have it, how we should calculate them. So let's see now what we have from problem statement. We had the probability that the year is going to be cold is 40%, and the probability that the year is actually going to be warm is 60%. We also knew that for those years that actually it happened to be cold, forecast also predicted cold 90% of the time, and in those years that actually it was warm, the forecast also predicted warm 80% of the time. Okay, so these all came from problem statement. Now let's see what is complement of this probability. Probability that the forecast says cold if the weather condition actually is cold is 90%. So that means that probability that the forecast says warm if the weather actually is cold is only 10%, right? The 10% and 90% are complement of each other. How about this one? If we know that the weather is actually warm, the probability that the forecast says warm is only 80%. What is complement of this one? Probability that the forecast says cold if the year is actually going to be warm, and that's 20%. So all these probabilities here on the top left came from problem statement. So now let's look at the problems that we need on the decision tree. I need probability of forecast saying it's going to be warm, or probability that the forecast says it's going to be cold, but none of these probabilities are given in the problem statement, as you can see. I need the probability that the year actually is going to be cold if the forecast says warm, or also the probability that the year is actually going to be warm if the forecast says warm. But as you can see, none of these probabilities on these terminal branches are the ones that we already have from the problem statement, right? So none of the probabilities that the decision tree wants are the ones that the problem statement has given us directly. So what should we do? We have to calculate these probabilities that we need on the decision tree from the probabilities that the problem statement has given to us, and that's where those conditional probability rules that I initially explained will come handy. So let's see now how we can calculate these probabilities that we need on the decision tree. So let's pick one of these probabilities. Let's pick probability of C conditional on FC. This means the probability that the weather is actually to be cold if we know that the forecasting has said it's going to be cold as well. Let's see how we can calculate this probability. So here we have the problems that are already have been given to us from the problem statement. I have put them on the top right corner of the slide, and we want to calculate probability of C conditional FC. So given the conditional probability rule, we can write this probability as probability of C intersection FC divided by probability of FC. Okay, so let's see how we can calculate these probabilities in the numerator and in the denominator. So let's look let's try to calculate probability of C intersection FC. So again, from conditional probability, I can rewrite this as probability of FC condition on C multiplied by probability of C, right? So we learned that from the conditional probability formulas, right? So I got the intersection probability that I have in the numerator, and I tried to rewrite it, but this time that I rewrite it based on conditional probability, I try to rewrite it based on the conditional probabilities that I already have in the problem statement. So instead of writing this as probability of C condition on FC, I'm writing it as probability of FC condition on C. Why? Because the probability of FC condition on C is something that the problem statement has given to me, so I can calculate this probability of this intersection. So right now, then probability of FC condition on C is something that I have from problem statement, that's 0.9, and then probability of whether it's going to be cold is 0.4, and then that gives me 0.36 as the probability of C intersection FC. Okay, so how about the probability of FC in the denominator? How we can calculate that one? We can write probability of FC, probability that the forecast says it's going to be cold, as probability of FC intersection W, meaning that the weather is going to be warm, plus probability of FC intersection C. Okay, we can rewrite each one of these probabilities based on the conditional probability. We can say probability of FC equals to probability of FC condition on warm multiplied by probability of warm plus probability of FC condition on C multiplied by probability of cold. Again, note that this probability, this intersection, I can rewrite it as probability of FC condition on W multiplied by probability of W, or I can rewrite it as probability of W condition on FC multiplied by probability of FC. But I pick the form that for which I have these actual probabilities from the problem statement. So I write it in terms of probability of FC condition on W because I have this probability of here. If I write it as probability of W condition on FC, I don't have that probability here. Okay, so that's how you find how to rewrite these conditional probabilities. So probability of FC condition on W, we have it here is 20% 0.2 multiplied by probability of W. What is the chance that the weather is actually going to be warm that year? 60% 0.6 plus probability of FC condition on C, that's 0.9 multiplied by probability of C, weather is actually going to be cold, that's 0.4, and the final results is 0.48. So the chance that the forecast is actually going to say weather is going to be cold is 0.48. So now that we calculated numerator and denominator, we can calculate the actual probability that we want. So that's 0.36 divided by 0.48, that's 0.75. So the actual probability that we need to put on decision tree is 0.75. So one other thing before we go back to the decision tree is that now that you calculated this, what is the complement of this probability? So remember, the complement of the probability never changes the condition part. So the complement of this probability is what is the chance that the weather is going to be actually warm if we know that the forecast has said it's going to be cold. Okay, so that probability is going to be 1 minus 0.75 and is 0.25. So now that we calculated this probability, we can easily calculate the complement of this probability of W condition on FC. And the reason that I calculated it right now is that we need both of them on the decision tree. So now we calculated one, we can easily calculate the other one instead of going through all the calculations again. Now I'm going to go back to the decision tree and put the values of these probabilities that I calculated on the corresponding branches. Remember, here was the probability of the weather is going to be cold. If the forecast says it's going to be cold, that's what we calculated, 0.75. And here was the probability that the weather is actually going to be warm if the forecast said it's going to be cold, and that's what we calculated as 0.25 as well. And here also in these two branches we had the two same probabilities, and I put the corresponding values as well. So what I'm going to do then is to calculate these conditional probabilities in the other 4 branches so that we can complete the decision tree. So let's assume we are going to calculate this probability of W condition on FW, meaning that probability that the weather is going to be warm if forecast has said it's going to be warm. So we can pick any one of these probabilities, it doesn't matter. So let's in this presentation, I'm just picking to calculate probability of W condition on FW. Okay, we can use the conditional probability formulation and write this as probability of W intersection FW divided by probability of FW. So let's see how we can calculate the numerator. For the numerator, we can obviously rewrite it as probability of FW condition on W multiplied by probability of W. Pay attention that I'm rewriting this probability of intersection based on the probabilities that I have in the problem statement. So then probability of FW condition on W is 0.8, and then probability of W that the weather is going to be actually warm is 0.6, and the results is 0.48. Okay, so that's the numerator. How about the denominator, probability of FW? I can write it as probability of FW intersection W plus probability of FW intersection C. The weather is actually going to be cold. So okay, so similar to the previous probability that we calculated. However, instead of going through these calculations, this time I can calculate probability of the FW in an easier way. One other way we can write probability of FW is write it as 1 minus the probability of its complement. What is the complement of probability of FW? What is the probability that the forecast says warm? The complement of that is the probability of forecast says cold. Okay, so I can write probability of FW as 1 minus probability that the forecast says cold. And if you go back to the 2 previous slides, we calculated probability of FC as 0.48. So we already have this probability. So I can just say probability of FW is 1 minus 0.48, which is 0.52. Okay, so in this case, I can calculate probability of FW in an easier way as opposed to going through the sum of these intersection probabilities. Okay, so let's just stick to this easier way and just conclude that the probability of FW forecast says it's going to be warm is 0.52. So by having the probability of numerator and denominator, the actual probability that we need is going to be 0.48 divided by 0.52, and that's 0.923. Okay. So one more thing again, before we move on to the decision tree, now that we calculated probability of W conditional on FW, what is the probability of the complement of this probability? That's going to be the probability of C condition on FW, and that's going to be 1 minus 0.923, and that's 0.077. Again, I calculated the complement of this probability because on the decision tree I need both of these probabilities. So instead of going through the whole calculations for this probability, I can just easily calculate it as a complement of the probability of W condition on FW that we already calculated. Okay. Now let's go back to the decision tree and put the probabilities that we calculated on the corresponding branches. So this is the probability that the weather is actually going to be cold, given the fact that the forecast says it's going to be warm. That's 0.077, and this is the probability that the weather is actually going to be warm if the forecast said it's going to be warm, and that's 0.923 that we've just calculated. And these two branches have similar probabilities, and I put them here. Okay, so the other branches that need probabilities are these four ones at the bottom, and then probability that forecast says warm and the probability that forecast says cold. Okay, so probability that the weather actually is going to be cold or warm were given to us in the problem statement. The probability that the weather is going to be cold was 40%, and the probability that the weather is going to be warm is 60%. So we are going to put those probabilities as well on the corresponding branches. And here the probability that the forecast says it's going to be warm and probability that the forecast says it's going to be cold. If you remember, they were not given to us in the problem statement, but we calculated them in the two probability slides that we did the calculations. These two were calculated as well. So if you go back to those slides, you will see that the probability that the forecast says is going to be warm is 0.52, and the probability that the forecast says it's going to be cold is 0.48. Okay, so now that we have the value of all the probabilities on the corresponding branches, the rest of the calculations is similar to what we did for the other decision tree. We are going to give a number to each one of these event nodes such that we know which one of them we are calculating. Next, I'm going to calculate the expected value associated with each one of these decisions. So here, for example, if I make the decision to plant corn, two possible outcomes will come, and each one of them has its corresponding value with the corresponding probabilities. So what is the expected value associated with this decision? Similarly, what is the expected value associated with the decision of planting wheat in this field? Okay, so I'm going to calculate the expected value associated with node 1, 2, 3, and 4 next. So the calculations are done here similar to what we have done for previous decision trees. Multiply the corresponding values by the probabilities and add them up. The final values of the expected value of each one of those nodes are written in this table. So I'm going to put these values back on top of the nodes on the actual decision tree. That way we can make the decision that if we ever are at this decision making point, what is the decision? Planting corn or wheat? We'll see that in this scenario, since the expected value or expected earning corresponding to planting corn is higher, so the better decision is to plant corn, and we expect to gain $7,169. How about here? If we ever are at this decision making point, what is the best decision to go with, planting corn or planting wheat? And as you can see, since planting wheat leads to higher earnings, expected higher earnings, we are going to make a decision to plant wheat in this scenario. Okay, so and then the value of these decisions would be $6,025. Next, we need to calculate the expected value associated with node 7, 5, and 6. So for node 7, we have the value associated with each one of these possible outcomes, and we know the probability of each one of them, so we can easily calculate the expected value associated with this event node, and that's going to be $6,620.2. And how about here? If we plant corn, two possible outcomes will happen. We know the value associated with each one of them, and we know the probabilities. So the value associated with each one of these even nodes can be easily calculated as well. And when we write the value of the expected value on top of the decision nodes, it can help us to make a decision if we are ever at this decision point. If I'm ever at this decision point, as you can see, based on the expected values that we expect to observe, there is no difference between planting corn or planting wheat. Any one of them can be a good decision. And so the value associated with this decision node is 6,800. And finally, if we are ever at this decision making node, what is the best decision? Should we pay for the forecast, or should we not pay for the forecasting of the weather? And as you can see from the values, the best decision here is not to pay for the forecast. And then from there, we can decide on planting corn or wheat. They won't make a difference, and we expect to gain about 6,800 as the value at the end of the day. Okay, so that's the structure of the decision tree, and that's what the analysis of the decision tree showed us in terms of what decision to make. So what is the expected value of sample information? Again, as you remember from previous example, to calculate expected value of the sample information, we obtain the value if we pay for the forecasting of the weather. That's the $6,620.2. However, we assume we are not going to pay anything for the weather forecast. That means I'm going to return the $600 that I deducted when I paid $600 for the forecast. So I'm going to return it back. So that value minus the value that we expect if we do not do the forecast at all, that's 6,800, and the final value is $420.2. So that means the maximum value that we are willing to pay for a weather forecast, and still it's worth it to use that information to make better decisions, will be $420.2. As you can see in this problem, they charge us $600 for the weather forecast, and that's why it wasn't beneficial for us to go through that route and do the weather forecast and go from there. The maximum value that we are willing to pay for a weather forecast and use that extra information to make better decisions is 420.2. So if you're charging us any value higher than that, it doesn't worth it.